Buenas tardes a todos, gracias por su asistencia. Les presento a Cristina Steele, quien nos presentará la charla de Future of Genetic Analysis, Advances in Systems for Cytogenetics and Fish. Ella es graduada del Diagnostic Genetic Programs de la University of Connecticut, trabajando posteriormente en citogenética, fish y patología. Luego se gradúa de MBA y actualmente trabaja en Applied Spectral Imaging y además en el Department of Clinical Laboratory and Medical Imaging en Rutgers Schools of Health Profession en New Jersey, enfocada en técnicas de FISH asociadas a citopatología. Dejo con ustedes a Cristina Steele. En la sección preguntas de la plataforma pueden dejarnos sus dudas o comentarios al finalizar la charla. Thank you, Cristina, for being here.
You're welcome. Thank you, everyone, for joining today's presentation. It is my pleasure to be invited to present at this conference. So I will begin with introducing applied spectral imaging for those that are not familiar with the company. The goals of applied spectral imaging is to develop biomedical imaging and analysis solutions for clinical cytogenetics, pathology, and research laboratories. The end goal is to optimize and improve patient care by providing accurate diagnostic tools. How ASI's programs and products are determined by specimen type. So for cytogenetics, for G banding, karyotyping, hyperspectral karyotypes, we have the high band product. High FISH is designed for any fluorescence in situ hybridization samples and their imaging. And CytoPower is the combination of both. Moving over to pathology, we have the HiPath Pro, which is designed to digitize and provide whole slide images for pathology slides, being H&E or IHC. And for IHC nuclear membrane stains, we have image analysis software as well. And merging together whole slide imaging with corresponding paraffin embedded FISH slides, we have the Path Fusion. Research, we have the Rainbow product that allows for hyperspectral unmixing imaging. ASI is a leader in digital microscopy since 1993. The world headquarters is located in Israel and in the US in sunny California. ASI offers direct sales in Canada, United States, and Israel, and partners with over 70 distributors throughout the rest of the world. In Argentina, we are proud to work with Instrumentalia as well. So with today's presentation, I will be reviewing the evolution of cytogenetics testing, and beginning in the 50s and 60s, where whole chromosome banding was utilized in order to organize the chromosomes literally by their chromosome size and length. With the evolution of banding techniques evolving in the late 60s and 70s, the field was exposed to Q banding, C banding, R banding, and what's most popular today, G banding for constitutional and oncology cytogenetic testing. During this evolution, in situ hybridization techniques were also being discovered and deployed with many different types of tags for targeting, where the fluorescence really took hold in the mid-1980s and became a valuable resource for researchers and clinical testing, evolving from there. And then in 1993, we had the evolution into spectral karyotyping, the merging together of FISH techniques and clinical classical cytogenetics. Other major tests also emerging throughout the evolution of cytogenetics includes microarrays, moving more into the molecular field of PCR and next-gen sequencing that are all extremely valuable to this entire field that's continuously growing and developing. But for today's presentation, I will be focused on slide-based testing. So Applied Spectral Imaging's first product release was hyperspectral karyotyping, or SCAI. As described by the NIH, SCAI is a karyotype process in which homologous pairs of chromosomes are manipulated in a way that they have distinct colors. The SCAI technique makes it easier for scientists or clinicians to detect chromosomal abnormalities as compared to conventional karyotyping. ASI is the sole vendor when it comes to the SCAI application, the image analysis software, and SCAI probe kits. ASI also has the availability to produce and provide customized whole chromosome paints for human or mouse testing. The goal and the clinical utility for SCAI applications are the unique capability to identify marker chromosomes, detect cryptic translocations, and resolve complex chromosomal arrangements. So how does the SCAI procedure work? So each chromosome is actually separated out and colored with a specific combination of a color set that we have designed at ASI. These 24 chromosomes with their unique color combinations are then combined into a master probe mixture. The laboratory will go through their process of obtaining metaphase cells and dropping them onto slides, and then using a fish hybridization technique to hybridize these paints onto these metaphase cells. Once the hybridization is complete, the slides are placed on a microscope that has the ASI optical head attached to it. This interferometer-based imaging process allows the image capture going through all the light range in the visible and infrared spectrum as well, in order to go through and identify the specific chromosomes based on their probe mixture combination. So here we have a case study where a sample was received for a patient with a diagnosis of mental retardation. Conventional cytogenetics was not able to provide any clinical diagnosis outside of a normal karyotype. But upon testing the sample with the SCAI procedure, we were able to detect a cryptic translocation of a derivative 5 chromosome that actually had a 21 on the P arm. Here we have a beautiful G-banded complex abnormal tumor. And with this evaluation with SCAI, we were able to accurately determine the complex translocations that were occurring throughout this abnormal tumor outside of the gains of chromosomes, as you see here. And for a neuroblastoma, where the chromosomes are very short and stubbing, can be sometimes very difficult to accurately place your numerical gains, we can also utilize the SCAI to identify the total number of gains of each chromosome itself and the unique rearrangements. Today, hyperspectral karyotyping is still being utilized in research laboratories and a few clinical cytogenetics labs as well. Here we have Dr. Jean Gu from the MD Anderson Cancer Center in Texas utilizing Sky karyotyping in his clinical cytogenetics training program there. Now we'll be moving forward to discuss fluorescence in situ hybridization. The challenges of manual FISH analysis. I can attest to being in a FISH laboratory in the darkroom for many years of my career. Manual FISH analysis is amazing, but then it also comes with its challenges. And being on the other side now as a imaging system vendor, I understand some of the hesitation with moving forward to FISH automation, and sometimes it can be personnel you're used to being at the microscope, or also financial restrictions. But just kind of reviewing some of the challenges currently laboratories face when dealing with manual FISH analysis. Many laboratories, the whole real estate, lack of real estate is a major issue. Being able to allocate a separate room and separate it from the other laboratory spaces so that it can be dark and isolated can be very difficult at times. And then we have the bottleneck of being able to have sufficient number of FISH microscopes. That has seemed to be a bottleneck in many laboratories where, for example, you might have 5 FISH technologists, but only 3 fluorescent microscopes. So there has to be a rotation of shifts to maximize the personnel to the number of microscopes present. And then there's the actual analysis itself. The tedious repetition of switching the microscope filters. A majority of the analysis can be performed on the dual filter of red and green, but on occasional you'll come across your probes where you have 3 colors or 4 colors, so that requires switching back and forth. Or you can have a difficult specimen with weak hybridization signals, so that you must need to go back and forth between the dual and single filters to really verify if there's a deletion or if it's just a weak signal. Then the actual capture process, manually capturing these FISH images on the microscope, going through the individual filters and being able to Z-stack, if your software allows Z-stacking when you're doing your image capture. You also might run into the issue where not every fluorescent microscope has a camera attached to it. So then you have to relocate your slide to a microscope with the capturing capabilities. And then the tendency for some FISH probes to weaken, quench, or lose the signal intensity during your analysis process. So you kind of have to constantly be moving around the slide and scoring pretty quickly, depending on your probe, to make sure that you don't lose that signal in case you need to return back and have someone verify your suspicions. And once you've completed your manual analysis, then you have to go through and tabulate your percentages for each signal category and figure out if you've exceeded the threshold to result this as positive or negative. Applied Spectral Imaging's scanning platform for digital FISH is kind of, the workflow is reviewed here in this nice schematic. ASI offers 2 types of scanners. Displayed here is a 99 slide high throughput tray loader scanner, but we also can provide a 9 slide scanner. So it's just the microscope with the 9 slide stage. It is modular so that you can start off with a 9 slide scanner, and as your volume increases or you add different sample types, one can easily add the tray loader as well during phase 2 of your growth of the laboratory. So this scanner, based on the barcode that's on the slide label, will recognize the patient, the patient identifiers, the specimen type, if it's a paraffin-embedded sample, urine, blood, bone marrow, which is the probe type, and how to do the scanning. Once the images are obtained in the review station, one can go through and review all the thumbnail images that were captured, and then review and approve the analysis for the cytogenetics director or pathologist to complete their sign out, and also use the ASI software to produce a report. When using the fish analysis scanner, we actually have created different modes of scanning fish slides, and these are customized based on each laboratory's sample types and what they're trying to achieve. So for suspension fish, urine, or cases that can have a variability of cell density, we recommend the density scan. So the microscope will start off at a 10x objective and scan the whole probe region first and identify the areas with the highest cellularity, so that it will return to those areas first with a high power objective to perform image capture. The scanner is set up to have stop criteria that are built in. So for example, it will stop after it has captured 400 cells, if that's your cutoff value, or 20 minutes. And we like to have a time limit as well, especially, for example, for urine samples that can be very low cellular samples. We don't want the scanner sitting there for hours trying to capture 400 nuclei if there's only 20 present. So once it reaches one of the two cutoff values, it will move forward to the next slide. For specimen types that are known to have a high cell density, we can recommend the spiral scan, which will start automatically on a high power objective and from the center of your target area and just capture until it has met its stop criteria of, example, 400 nuclei. For quality assurance purposes, we have a workflow that will scan metaphases and nuclei at the same time, and I'll go into more detail later. And also a double-blinded analysis workflow, where the scanner will not automatically place the cells based on their signal pattern. We leave that up to the technologist. So one of the main focuses ASI has when creating these robust imaging algorithms and platforms is to assist the fish laboratories transition from manual to automated. It's difficult for some people to leave the comforts of the microscope. So we want to make sure that making that transition, what we display on our screens match as close to what you're seeing under the microscope and how the microscope functions. So we have digital Z-stacking and 3D image review. So as the scanner is capturing each individual filter, it's actually going through and Z-stacking. And these Z-stacking layers are customized by the lab and can be different between sample types. So you would want more Z-stacks on a paraffin tissue than is required for a cell suspension. Then when you're also reviewing your individual fish images, you can have the composite of all the individual filters together in one image, but sometimes that can be too much information upon your review if you have, for example, in this image, 4 probe colors and DAPI. So underneath that cell, we actually separate out all the different filters so your eye can immediately go through and review the DAPI separate from the aqua, green, red, and gold. It's very easy to then digest the signal patterns when they're kind of separated out. And then there's also, for those wanting the software to do automatic cell detection and classification of the cells based on their signal patterns. So the software is programmed with many different mathematical figures to try to accurately place these signal patterns correctly. And that's based on signal intensity, signal size, and also the spacing. So when to call one red signal 1 versus 2 that are side by side, are those 2 red signals one splitting, or is it actually 2 individual reds? So all of those go into the algorithm on how the software does make its final decision. So reviewing the interface and metaphase scan, the end user will tell the scanner, I would like to capture 100 nuclei and 10 metaphases. So while it's going through its scanning process, it will complete both requests in the same time. And when you're in the review screen, you're able to toggle back and forth between those 2 cell types. So when interface is pressed, you'll see all the nuclei that were captured under interface mode and how they were also categorized. So here, this is a HER2 new fish probe. That's probably a new lot validation. And so some of the typical patterns that they were looking for is 2 reds, 2 green, and that is, you'll see the statistics on the bottom left-hand side of how many cells fell into that category and the other categories as well. By toggling onto the metaphase tab, we're able then to switch and review the metaphases that were captured for this probe as well. Now, there are different workspaces as well. So you can see here, I was able to actually enlarge the metaphase so I can do a little bit more analysis and see it kind of zoomed in. So these are very different ways that ASI's workspaces are flexible, and one can literally create and shift things around in the window to maximize and make it easier for your image analysis. So here we have a beautiful metaphase where you can see that, the green is at a centromere location of a chromosome, and the HER2 red is looks like a Q arm, but is it really, chromosome 17? We're able to do DAPI inverse and revert it so that we can kind of see the bands that are naturally there with a DAPI metaphase. So this way we can, confirm, yes, this is chromosome 17. For the double-blinded workflow analysis, this is something that is unique to ASI and have found it to be very popular with fish laboratories that are ready to transition to automation, but not ready for the software to do the image analysis 100%. So with this workflow, it's very similar to what's occurring in their lab current state, where the power is still in the technologist to do the analysis of these cells. And so, but providing a benefit that it is truly double-blinded. So the scanner will just go through and capture the 400 nuclei that you've asked it to capture, and it will list them from 1 to 400. So a technologist will log into the software and start placing the cell into its appropriate signal category. So the software is keeping track of your percentages of each signal pattern for you. And once the end user has met their 100 classified cells, a notification appears on the screen. You've completed 100 cells. Please approve for analysis. They approve the analysis, and the status for the case updates to second review needed. The second user logs in, and they are completely blind to what the first tech observed. They do not see their statistics. They do not even see the cells that the first tech analyzed. It's completely blind. They will start at cell 101 and complete their 100 cell review. Once the second tech has completed and approved their analysis, that's when the software merges the first 100 with the second 100 and shows you the combined statistics. There's also a feature that we can put in there. If there is a % difference of the signal pattern between score 1 and 2, the software will automatically generate a status saying third score required. And so then you complete the process with the third score, and you can decide which 2 scores to keep if you don't want to report out 300. Now moving to paraffin fish. We actually have developed an application that merges the pathology whole slide imaging and having it correspond to the pathology fish slide. We have found that this area of fish testing is growing very quickly and rapidly, especially due to the increased need of companion diagnostics and requiring a fish result in order to provide therapy for the patient. For example, HER2 or ALK and ROS for non-small cell carcinoma. So the way that this workflow is designed is the bright field pathology slide is placed on the ASI scanner. And while that is scanning, the pathologist can log in and digitally mark the tumor regions on the pathology slide. Once the fish department is completed their fish processing of their slide, it's placed on the scanner and a low power scan is completed. The technologist will match the fish slide to the pathology slide. Once they're matched, the tumor regions will transfer from the pathology slide to the fish, and the high power scanning will occur on those fish tumor regions. Then the technologist can log in, review the fish frames, approve it for analysis, make any updates, so that the pathologist or director can log in and actually have a new tool that allows them to review the fish frames side by side with the corresponding bright field pathology slide. And then report the case and create a custom report from the ASI software if desired. And we also have a few different scanning modes available specifically for tissue fish. So the first one, as I just previously described, matching with a pathology slide. Our first adventure into AI and deep learning algorithms is the workflow of automatic tissue identification and scanning, which I'll go into that briefly in the next few slides. And for those laboratories that have the fish scanner but do not have the bright field imaging, whole slide imaging capability, you're able to scan the whole slide for the paraffin fish under low power and then manually pick the areas where you desire the high power image capture to occur. And just how we always strive with all of our imaging products is to make our images as natural and easy to review so that it mimics what one sees under the microscope. With our IHC module, I'll just quickly go over this one slide. We started off with just being able to match bright field to fish directly, but not bright field to bright field. So actually last year, we developed this module that allows pathologists to match their reference pathology slide to the additional stains that are requested on the same case, and then have the tumor area relocate to all the other stains as well, and also do image analysis review on multiple slides in the same screen. So here we can accommodate up to 4 slides at the same time. We indicate landmark regions to areas that are exactly the same location on all the slides. Once that landmark locations are placed, the system is able to place all the slides together in sync so that when you zoom in or zoom out of one slide, the corresponding 3 behave with that same action. And also, the scribed areas from one slide populate across the entire case. And then we can perform image analysis. Here we have membrane and nuclear stains, and you can see the results for each stain for this case. We also have the flexibility to add and remove different slides for analysis because you might have more than 4 slides on this pathology case. And when it comes to image analysis, there is the option to review the statistics for one specific region, especially in cases with tumor heterogeneity, and the overall slide itself. So you can distinguish between the 2 individual regions and then the complete review of all the regions that were analyzed. And then if this IHC case, a pathology case, is reflexed to fish, one can add the fish slide and have the tumor areas that were initially analyzed on the pathology slide add directly to the fish. The deep learning automatic tissue detection and capture workflow is recommended for small tissue pieces that are mostly tumor. And for this workflow, the slide is placed on the scanner. The scanner will do a low power scan of the entire slide, and the software will automatically detect the tissue sections present and then go back under high power objective and capture the entire tissue section present. And also when it comes to image analysis, we now have produced 2 different analysis workflows due to feedback of end users. Previously, as the tissue section was being captured under high power, we had the software automatically performing cell segmentation and signal quantification for each cell. Specifically for HER2 fish, some laboratories want to follow the CAP-ASCO guidelines and report out a specific number of cells, be it 20 to say 50 or 60. But if the scanner was automatically doing cell analysis, you may open up a case and it already has 400 cells analyzed. So then you'd have to go and delete 350 cells in order to meet your specific 50 cells you want to report. So we've actually taken a step back and incorporated a new workflow that the scanner can go and just capture the number of frames in each tumor region without analysis, so that the technologist, when logging into the case, can review the frames that were captured and select the 1 or 2 frames where you would want image analysis to occur, and then run the analysis software on that specific frame so that it makes their life easier at the end. So here I actually have a brief video of this whole pathology and fish analysis workflow. I could spend over an hour going through all the details and features and tools, but I will not because of our time limits. So I apologize in advance if you'd want to see more. I'm sorry, this is going to be a very brief overview. So we start off with our case data manager. All ASI platforms have this window where we list all of the cases in the case menu. And when you select a case, the demographics and information appear at the bottom left-hand side. Also the slides that are associated with that case. And when you select the slide details also populate. And we have built-in tracking so that you can see what status each slide and the overall case is in. So here we will be reviewing an H&E case with a HER2 fish. So this is a technologist logging in. They have reviewed that the pathologist has already digitally marked the tumor regions on the H&E, and now they will go through and digitally mark the two landmark areas that are the same on both slides. So we try to find areas that are very distinctive but easy to locate. Try to make this very easy for the end user. And once those two areas are marked, the software will actually rotate the H&E slide a little bit so it matches completely to the fish, and those tumor regions are populated. But this being a real life case, there is, shifting of the sectioning of the tissues, so we can move areas as needed, as we saw here with section number 5. So now the scanner will go back and under high power capture those 5 areas that were indicated by the pathologist. So the technologist actually logs into the scanner review station now. You're able to actually open up the image to see where the frames actually were captured in each tumor region. So this lab decided every region will have 4 frames captured. And this was performed with analysis. So all 20 frames that were captured were analyzed, and we have 364 cells. And we have different ways to show the statistics. So here's an amplification histogram with the total number of red and green. Classes based on the CAP HER2 guidelines of groups 1 through 5. Just signals, red over green. And a signal map that lists the total number of HER2 over green and the number of cells that fall into each category. As the software completes image analysis, it will highlight the cells that it has identified and classified and color code them based on their class. When we click on a cell in the large frame, we can actually highlight it in the smaller viewer to be able to see how the signal count was. So for that cell, 3 greens, 24 reds, the multicolor panel, so the separate DAPI, red and green. And you're also able to go through and enhance the colors to brighten them up or darken them. And here is what I explained previously, the 3D review. So you're able to go through all the different Z stacks that were captured for each individual color. And you can do that, as we saw in the beginning, for all the colors combined. And so this is, I find, extremely helpful when trying to determine, is the signal real or not. The 3D ability to zoom in and out is very similar to what you're doing currently at a manual microscope. So then the technologist will go through the other frames and pick out, their results and how they want to complete this case for the director or pathologist. Now the pathologist will log into Tissue Suite, and they're able to see the overview of the results of this case, the probe name, the amplification ratio, average red, green, total number of cells, and how these cells are designated into each group category. The display options are vast, so you can have a window of 4 images or highlight 1 to see the analysis display, the original display, how it was captured from the microscope, versus the enhancement or photoshopped image, just to allow you to visualize those signals much easier. Then when moving from frame to frame, you can actually toggle up top through each region or frame, or actually go to the slide on the left-hand side, zoom in, zoom out, and select the frames themselves by highlighting that region. And you can do that on the fish side as well. You have all these flexibilities. Then at the end, if you go to the summary tab, if you had multiple slides here, you would have a summary of all the slides and their statistics. And at this point, you can write out your interpretation, final diagnosis, and create a final report. This is an example report template that is, generic, but a good starting point for many laboratories to build upon and make this better as they need for their lab. So where ASI is going in the future with fish innovation and bringing in more artificial intelligence so that we're always improving this product and moving forward as needed in this field. So where we are moving with these AI-based algorithms is constantly improve the image quality just to make sure that the end user is 100% comfortable with what they are viewing and reviewing. Improving the signal visualization, which will allow the software and the end user to be able to more accurately perform signal detection. And with this deep learning model, it will be optimized per each individual lab and per your specific probe. So it is learning as you are correcting the software. Some examples of already the AI being tested in our R&D department. Version 8.2 is what's currently out there, and that's a few images are listed on the far right-hand side. And we've created a new enhancement Photoshop kind of layering that it has the AI development behind it that will target to produce a more accurate fish signal that is present under the microscope, and to avoid the background populations that sometimes interfere with how these images are enhanced. And so you can see the vast difference between image on the right-hand side and the left using the AI enhancement mode. And last but not least, we will now discuss G-banding. So evolution of cytogenetics analysis actually started with their own version of a darkroom, and that was using film cameras and actually developing your metaphases on photography paper, cutting them out with scissors and placing them on a karyotype table. I never did the photograph development, but I did learn on cutting out chromosomes and placing them on a karyotype table. These are one of my early karyotype tables back from when I was at the University of Connecticut, learning my chromosomes and ISDN and how to determine the band levels. And this technique was very time consuming. You would have to print out several metaphase photographs to meet the needs of overlapping chromosomes, and inevitably I would lose a chromosome in my hair and it'd be stuck there because I just have a lot of hair. Then we have the emergence of digital cameras. And from here, we were able to move out of the photography darkroom and being able to capture these metaphase images with digital cameras, and also the development of digital karyotyping software on a computer. I love this image because it brings me back into the 90s with the big box PCs. And where we are today, metaphase automated finding, capturing, and being able to karyotype on the software. So an example, the metaphase scanner will go through on 10x, find all the metaphases and relocate to the specific number of metaphases it's designed to relocate to. And it can be based on quality or 1 through 20 if you're doing oncology. Then as these cells are being captured on 100x, they're available immediately in band view for karyotyping analysis, counting, indexing. ASI has the magic tool, which is superior for chromosome karyotyping because it allows you to perform 12 actions with one tool, overlapping, splitting, extending, combining. It's so much easier than having to have separate tools to complete these actions. And when you are working on an abnormal case and you're scratching your head and you're trying to figure out what this abnormality is, we've incorporated a list of the most popular cytogenetics websites that you can immediately launch from your band view and review and compare to the chromosome you are questioning. And then once you've completed your case and you want to review your karyotypes to make sure there are no errors, or you're questioning a particular chromosome or translocation, you can go to Chromosome Compare and it lists all the karyotypes for that case. And you can section it off too to only say you have a 922, so you can just show the 9s and the 22s together. Or you're questioning in version 16, you can highlight just the 16s. If it's a parental lineage study, you can actually bring in the father, the mother, the child, and have all three karyotypes together to review. And for those doing multi-species testing, we also have that capability as well. So where ASI is going in the future when it comes to cytogenetics is also bringing in artificial intelligence. So ASI, developed the groundbreaking Sky karyotyping techniques, and we want to revisit with our groundbreaking software when it comes to cytogenetics with this new module for artificial intelligence. So here, this is going to be released very shortly within the next 6 months, where we have the high power scanning occurring, and as the 100x is being captured on these metaphases, the software, the software will actually go through and cut out the chromosomes automatically and place them in the karyotype table, so that as it's even going through the slide capture, you're already getting karyotypes immediately while it's not even done capturing that specific slide. It will have a new analysis state of automatic karyotyping. And in the gallery view, you'll be able to see the original image, enhanced, and karyotyped together. In band view, you can log in to be able to make any updates and changes as necessary, and provide you with the capability to automatically create the report and send it out to your LIMS system or the requesting physician. So with this, we are bringing karyotyping into the future with AI-based algorithms. And with that, I would like to thank everyone. Gracias, obrigado. Thank you for attending this presentation. For any questions that you may have, please reach out to Applied Spectral Imaging at sales@spectral-imaging.com, or you can visit our website at www.spectral-imaging.com. And I'd like to thank our distributors, our partners in Argentina, Instrumentalia, for today's presentation. And please, if you are in Argentina and would like to know more about ASI, please reach out to them. And here is their information as well. So Dr. Gonzalez, if you're ready to share any questions that might have come in.
Thank you, Cristina, for your interesting presentation. Queda abierta entonces la sección preguntas para Cristina a través de la plataforma de preguntas. Cristina, I have a question. When you perform the Sky analysis, how do you are able to determine the specific position of the breakpoint in a case of a translocation?
So the breakpoint itself is not going to be able to be specifically determined because of the whole chromosome paint, but the software is able to estimate the band level of when it happened on with the software. It's not going to be exactly accurate, but you're able to determine at what point this fusion occurred.
So it works like a G-banding.
A little, yes, yes. Because we are able to do, yes, because when it's actually being captured, you capture that metaphase on DAPI. So with the DAPI inverse, you're able to then estimate the translocation and combination with Sky.
Okay, thank you.
So it is, yes, sorry, it is possible. It's with that inversion of the DAPI.
Thank you, Cristina. ¿Alguna otra pregunta o comentario para Cristina desde la audiencia? Bueno, si no hay consulta desde la audiencia, Cristina, te agradecemos tu presentación. Thank you very much for your interesting presentation. Y el público queda invitado para las próximas actividades de nuestro Congreso. Muchas gracias.